All right, let's dive right in. Today we're talking about an experiment that the great physicist Richard Feynman said holds the absolute heart of quantum mechanics. Seriously, he claimed it contains the only real mystery of the quantum world. So let's see if we can crack it.
But before we get into any of the details, I want you to just keep one question in the back of your mind through all of this. It sounds simple, but it's the key to everything. And that question is, what is actually happening when no one is looking?
Okay, let's start with the basic setup. In this first part, we're going to run through the experiment and see a result that honestly just seems flat out impossible. It completely defies common sense.
So let's start with what we know from our everyday world, right? Things are either particles, like baseballs, or they're waves, like ripples in water. If you throw a bunch of baseballs through two big openings, you get two clumps on the wall behind them. Super simple. But if you send water waves through, they spread out and interfere with each other. You get this complex striped pattern of peaks and valleys. So particles make clumps, waves make stripes. Got it?
Now, an electron, well, it's a particle. It's a tiny little thing with mass. We can measure it as a single object. So it stands to reason if we fire a bunch of electrons at a barrier with two little slits in it, we should get two simple bands on the screen behind it. Just like the baseballs. Makes sense, right? Yeah, but that's not what happens. Not even close. We get a wave pattern. These electrons, these tiny little particles, create a series of stripes on the screen, exactly what water waves would do. It's as if these solid little things are somehow acting like waves and interfering with each other. And this is our first huge clue that the quantum world, it just doesn't play by our rules. Okay, so maybe there's a simple explanation. Maybe the electrons are just bouncing off each other after they go through the slits, and that's what creates the pattern. It's a fair question, so let's test it. Let's make it impossible for them to interact. So to do that, we can literally slow our electron gun way, way down. So slow that only one single electron is in the machine at any given time. One leaves the gun, travels, hits the detector, and only then do we fire the next one. There's no way they can bump into each other now. So we should definitely get those two simple bands this time.
But what happens next is just wild. As you can see here, the first few electrons land in what look like totally random spots. After 100 or so, it's still just a random-looking mess. But as we keep going, firing them one by one, thousands of times, that same wave interference pattern slowly, magically builds up, dot by individual dot.
The implication of this is just staggering. I mean, think about it. Each electron traveled completely alone. The only way that interference pattern can form is if each single electron went through both slits at the same time, as some kind of wave, interfered with itself, and then landed on the screen as a single solid particle. And this right here is exactly why Richard Feynman said what he did. This one bizarre result, the particle that is somehow also a wave that interferes with itself, that's it. That's the central puzzle of quantum mechanics. Everything else is just trying to make sense of this one experiment.
So if a particle is somehow going through both slits at once, the next logical step for any good detective is to try and catch it in the act. Let's spy on it. Let's find out which slit it actually goes through.
The setup for this is pretty straightforward. We just put a tiny little detector at each slit, something that can tell us, yep, an electron just went through here. Now we'll finally know for each and every electron which path it took. Mystery solved, right? Nope. The moment we measure which slit the electron goes through, the interference pattern completely vanishes. It's gone. And instead, we get exactly what common sense predicted from the very beginning. Two simple bands, just like the baseballs. The very act of looking, of knowing which path it took, forces the electron to stop its weird wave behavior and act like a normal particle again. This whole phenomenon has a name, the observer effect. And it's not like our detectors are just clumsy and bumping into things. In the quantum world, the very act of measurement is what changes the outcome. It forces the system out of this fuzzy cloud of possibilities, that's the wave, and snaps it into a single, definite reality. That's the particle. Before we looked, it could have been anywhere. The moment we look, it's right there. If you think that was weird, just buckle up. Because this next part pushes our whole idea of cause and effect right to the edge. What if we decide whether or not to look after the particle has already passed the slits? This is called the delayed choice experiment, and this timeline here breaks it down. So look, at point 1 in the past, The electron has already gone past the slits. It's in that weird, undecided wave-like state. Then, at point 2, in the present, after the event has already happened, we make a choice. Do we turn on our detectors to see which path it took, or do we leave them off? The absolutely mind-blowing result is that the pattern it makes on the screen later, at point 3, depends entirely on the choice we made at point 2.
Let me just say that again, because it's completely nuts. Our decision, made right now, appears to reach back in time and determine how the particle behaved in the past. If we choose to look, it acts as if it had only gone through one slit all along. If we choose not to look, it acts as if it went through both. Our present choice dictates its past.
Now, for decades, that was the standard, baffling story of quantum mechanics. But, science never stands still. And some more recent, really comprehensive experiments have added a huge new plot twist, suggesting the mystery might be even deeper and maybe different than we ever thought.
So here are a few key findings from some newer experiments by a researcher named Hui Peng. They found some really unexpected stuff, like they could block some of the stripes, the fringes, from forming, while others formed just fine, which is weird. They also found that putting long shields between the slits and the screen didn't mess up the pattern at all, which you'd think would happen if a wave was spreading out through space. So this has led to a couple of competing ideas. On the left is the standard story we've been talking about. The particle is a wave of probability that collapses when it's measured. But on the right is a newer interpretation. It suggests that photons are always particles. The slits just act like a kind of sorter, funneling them into different streams that travel in straight lines to make the pattern. The wave-like stuff only happens in a tiny little virtual box right at the slits.
So, what's the big takeaway here? It's that this experiment, the one that supposedly contains the only mystery, is not settled history, not by a long shot. It's an active, ongoing investigation, and new data is constantly challenging what we thought we knew. The story is definitely still being written. And that brings us right back to that first question, but now it's loaded with almost 100 years of mind-bending results. If the act of looking, of measuring, is what forces reality to pick a side, then what in the world is reality doing when we're not looking? What is the nature of the universe when it's left to its own devices? And that, right there, remains the deepest question of them all.